So welcome back. In the video on averages, we saw that it looked like there could be a relationship between the distance from the repair center and the total turnaround time. You can see that here in this chart. The average turnaround time for customers from Atlanta is about 6 days, and for those from Miami, it's nearly 25 days. Let's see if we can confirm that relationship and describe it with more precision. We're going to use a technique called linear regression. The topic can be quite complex. At some universities, there's an entire upper division course on this topic. But we can cover the basics from an intuitive perspective in less than 10 minutes. First, we need to plot the total turnaround time in days as a function of or against the distance. So the total turnaround time in days will be on the y-axis, and the distance from the repair center will be on the x-axis. And each point on the chart will represent a data record. So let's return to the raw data on this worksheet down here, raw data. The data for the distance is in this column here, column E. And the data for the total turnaround time is over to the right in column L. To make it easy to use the Excel chart function, it's best to copy the data to a new worksheet. So let's first copy the data for distance. So I'm going to the top of the column. I'm using Shift-N down to get the data. Control-C. Click down here to create a new worksheet. Right-click for the context-sensitive menu and choose Paste Values. Let's go back to the raw data and look at the total turnaround time. Go back to the top of the data. Shift-N down to get the entire column. Go up just one. I don't want the average. Control-C. Move over to sheet 2. Go to B1, right-click, paste values. Let's rename this worksheet tab Data for Line Fit. Now click on cell A1 and use Control-A to select all of the data. Now we're ready to make the chart. Click on the menu tab Insert, go to this section on Charts, and select the scatter charts right here. You might not see it because the icons shown depend on the width of your screen. If you don't see it on your screen, click here to see all charts. Go to all charts, click on XY scatter, and we want this one. Excel creates the chart. I'll make it a little bit bigger. Now we can see a general trend. As the distance from the repair center increases, the total time increases. That's not too surprising. So now let's add a trend line to the chart to show the relationship between distance and transit time more clearly. So we click on the plus icon, go down to trend line, click on the little triangle to the right to get more options, click on more options, and we want to display the equation on the chart and go down to the bottom, display R-squared value on the chart. I'll explain the R-squared value in just a minute. So here's the equation for the trend line. Y, which is the transit time in days, is approximately equal to 0.035 times x, which is the distance in miles, plus 7.65 days. Let's put that formula into Excel and see how it works. First, we'll make the estimate for 500 miles. In this cell, we'll put in the formula. So we start with an equal sign, as we always do for formulas in Excel. We type in 0.035 times x, which in this case is 500 for our example, plus 7.6536. It should look like this in the formula bar. Excel calculates that if there were a new customer located 500 miles from the repair center, on average, it would take 22.9 days, or about 23 days, for them to receive the repaired product back. Looking at the chart, we can find 500 miles here. We can go up to the line, and then over to the y-axis, and we can see, yes, about 23 days. If a new customer were 600 miles away, our estimate is 25.95 days. So we can go to 600, up to the line, and see, yes, that's right at about 26 days. Now this is the so-called best fit line. How does Excel calculate it? It uses the math from linear regression, a branch of statistics. Now, since this is not a math class, I'll skip the details. Suffice it to say that from an intuitive perspective, it minimizes the distance between each of the data points and the line. In other words, this is the best line of all possible lines because the overall error between the data points and this particular line is minimized. But how good is this so-called best fit line? The R-squared value gives us a rough estimate of the reliability. If R-squared were 0.0, it means it's completely unreliable. R-squared of 1.0 means it's perfect. From an intuitive, but not a mathematical perspective, think of the R-squared value as a means to explain the variability in the data as a percentage. In our case, 0.597 means that about 60% of the variability is explained by the best fit line, which isn't bad, but it's not great. If it were 0.85 or 0.9, that would be much better, explaining 85 to 90% of the variability in the data. But we can definitely see the linear relationship, and it confirms our common sense. As the distance increases, then the turnaround time increases, often to unacceptable levels of greater than 2 weeks.